Running is one of the most common movements in sports around the world. From basketball to soccer to cricket, most ground sports involve some form of running or sprinting. In some competitions, like lacrosse, athletes constantly restart short, dynamic sprints on a flat surface. In others, like skeleton, competitors only sprint at the very beginning. Sometimes restarts are controlled, like the start of a football play, but only a small subgroup of sports use specialized starting surfaces or equipment, such as swim starting platforms or track races under 400 meters. So, what exactly are the benefits of angled starting blocks? How do they work? And if they are so useful, why doesn't every sport use them? In this video, we'll focus on sprinting and explore how starting blocks work, what advantages they provide, and how they compare to starting from a flat surface. To understand sprint mechanics, let's start with analyzing jump forces. When someone jumps, they push into the ground and the ground pushes back, with the normal force coming directly out of the ground. This normal force propels the body upward, away from the ground. On a flat sprint start, the athlete pushes off the ground to propel themselves forward. When they push into the ground must respond with some equal and opposite net force. Runners push at an angle to induce a response force that propels them up and forward, unlike the jump that is purely up. Like this, the net reactive force splits between the perpendicular normal force, like the jump, and the force of static friction. This friction force is what propels the body forward. With an angled start, the normal component of the ground's response propels the foot forward too. As the foot pushes directly into the angled block, the only response is a normal force that pushes the foot along the path of its stride. Any frictional force would only serve to prevent the foot from sliding during the push. We must also understand the foot's path during a stride to analyze the overall biomechanics at play. At the start of the stride, the back foot rotates around the knee, up and forward. As the foot reaches its maximum height, the knee drives forward and the foot rotates in the opposite direction as the knee extends in a combined rotation-translation motion shown in yellow. Once the athlete extends their knee, they can plant their foot and drive into the ground for their next stride, shown in green. For our analysis, we simplify the foot's motion to a symmetrical arc, shown in blue. These mechanics indicate that sprint speed is largely dependent on the foot's angular velocity. Since the entire body starts from rest, the sprinter must optimize each foot's angular acceleration to reach their top speed as quickly as possible. With this focus on the foot's angular acceleration at the start of a sprint, we will analyze how the starting block improves this angular acceleration relative to the flat start and how this affects the body's overall translational acceleration.
So the first set of tracker data is going to be the translational motion of one of the sprinters. And so for this example, it was one of our sprinters using the blocks. And so you can see me setting a coordinate to his hip as well as using the calibration stick for the 1 meter that Carol was holding up right behind where he was running. And so I'm going to track him as a point mass as we did in the lab. And you can see that I sped up the video until it was to the frame right before he was about to start running. So this just ensures that the time starts at 0, but the X values are accurate. So you can just see me continuing to press on the same part of his hip that I set the coordinate to. And this is just going to pick up his translational acceleration, so just like his forward acceleration. Nothing angular here. That'll be something we talk about a little bit later. But I'm just going to continue to do this until he gets to the end. Okay, here I am going to do the angular acceleration. And to do this, we have to track a part on his foot, so I'm just choosing the middle of his foot, as you can see in the video. I chose his rear foot just because it's the one that moved first. So you can just see me continuing to click on this foot throughout tracking, and you can see in the Y graph we get kind of hills almost, and those will represent each of his strides. So when Kara talks about calculating angular acceleration, you use that distance traveled as well as um, the stride length. And so you can see me go through all of this, just continuing through the part of his run. And then all of this data can be transferred right into Google Sheets or Excel in order to do all of the calculations.
We will now be calculating the acceleration for both translational and angular. So tracker gives us the horizontal position and the vertical position and the time of the sprinter, but we only need the horizontal position and the time in order to find the velocity. Using these, you can do your change in position over your change in time to get your velocity. Use those different points to create the scatter plot chart that you see here to the right. Create a line of best fit in order to get that velocity equation and use that equation to find the acceleration. Our first sprinter we used was Will. As you can see, his two velocity scatter plot graphs are right here shown, with the flat start being on top and the angled start being on the bottom. Taking these scatter plots, you can create your line of best fit, and the equations are both circled here on top. You just take the derivative of your velocity equation in order to get that acceleration. And you can see that Will's angled start had a faster acceleration, with his flat start acceleration being 3.25 minus 1.034 times time, meters per second squared, and his angled start was 4.20 minus 1.922 times time, meters per second squared. Our next sprinter was Brian. He showed the same trends here, with his angled start being greater than his flat start in acceleration. Both of his scatter plots are shown here of the velocity versus time. Same thing, you just take the derivative of your velocity equation in order to get that initial acceleration. His flat start had an acceleration of 2.23 minus 0.222 times time, meters per second squared, and his angled start was greater, with an acceleration of 3.04 minus 1.214 times time, meters per second squared. Our third sprinter was Drew. He had his velocity graphs both shown here. Same concept, just take the derivative of the equations given from the polynomial line of best fit of the scatter plots. And you also see that his angled start was much faster than his flat start, with that acceleration being 3.54 minus 1.322 times time, meters per second squared, and his angled start acceleration was 4.74 minus 3.74 times time, meters per second squared. Now, our next sprinter has a little bit different data, and there are reasons behind this. We have seen that the angled start coming off of the blocks does require certain mechanics and certain mobility, like training stuff, to where all these three sprinters that you have just seen the data of are all athletes here at Union College. So they have all undergone strength and speed training. So they all are able to utilize these blocks to the best of their ability to be as efficient as possible. This next sprinter hasn't undergone any of that speed training, so going off of these blocks is not as natural or as useful to them. So our last sprinter was Adam, and his flat start velocity was actually much greater than his angled start, as you can see. Taking the derivative of the velocity equations given by both graphs, his flat start was greater at 4.15 minus 1.582 times time, meters per second squared. Then you have his angled start with an acceleration of 3.47 minus 1.252 times time. So again, his flat start had a greater acceleration, which is most likely accounted for the fact that he had never used these blocks before and hadn't been speed training like the previous three runners. So it was an unnatural movement to his body, which shows why his flat start was faster. So now that you have that type of acceleration, now calculating the angular acceleration of the runners, you do this through many steps. You first find the stride length, which is just your change in position. You find the distance your foot traveled, which is that change in position times pi divided by 2. And then you use that to get your angular speed, which is just that distance over the change in time. Just like before, Your acceleration is just the derivative of your velocity, so you can find your angular acceleration with the change in angular speed over your change in time. So this is a graph showing the comparison of the angular acceleration between a flat versus angled start for Will, our first runner that we displayed. All three runners showed similar results in their angular acceleration, given that their flat was actually a little bit higher than their angled. And that is just shown because the flat start produced a higher peak of angular acceleration earlier in time. This could be accounted for many different facts. I mean, angular speed depends on the individual's leg and the individual's own hip and knee joints and their own training. And all three of our athletes are all on different sports. So they all have undergone different types of training in all speed and strength and mobility and all that stuff. So they all have different angular accelerations to fit what their body needs best. So all of our runners will have different angular accelerations and they won't all be consistent with one another because it depends on the individual themselves. So this actually showed that for Will, his flat start produced higher angular acceleration. That makes sense because while Will's translational acceleration was higher with the angled start in the beginning, he is actually a distance runner on the track team, so he is much more used to starting flat-footed, which gets that angular acceleration to be a little bit higher for him when compared to angled. But again, it really all depends on the individual. So the angular acceleration doesn't necessarily come into play and is not a big factor in determining how translational acceleration is affected and the actual speed of the runner itself is affected on the flat versus angled start.
In this analysis, we identified how runners perform their initial strides differently depending on the angle of their starting surface. We found that acceleration is optimized with an angled start. However, this advantage is limited to the beginning of the race and becomes negligible over long distances. Especially with untrained sprinters, the difference between a flat and angled start is incredibly difficult to discern. However, the most important takeaway is that starting blocks are not just tools used to help athletes in their sport. They're also part of the sport. Knowing how to properly use a starting block is crucial to reaping any benefits in initial acceleration. Otherwise, you get something that looks like this. Needless to say, any advantage disappears for untrained athletes who could not provide the right initial form and push for a strong start. With these findings in mind, it's clear why start-dominant sprint events such as bobsled and the 100-meter sprint utilize an angled starting position and why it would be overkill in other sports. Not only would it add another aspect to an athlete's training, but it could also lead to complications on the field, court, or any other playing surface. More broadly, this analysis shows how even a small change in an athlete's starting position can affect their performance. Although an angled start may only provide a brief advantage, in sports where fractions of a second matter, that initial improvement can make a meaningful difference.